Hello, I'm Swathi. I'm here with Apoorv and Vinay today. We introduce to you ObitoNet, a multimodal high-resolution point cloud construction model. Point clouds are actually clusters of points in 3D. It is widely used in fields like robotics, computer vision, and many more. Generating high-resolution point clouds is very challenging. The data can be sparse or incomplete, especially when it's created from images. This leads to a patchy and low quality results. To tackle point cloud reconstruction, earlier works based on PointNet focuses on learning representations for unordered point sets. More recent methods such as PointMAE introduces the masked auto-encoding philosophy to point clouds, where a model learns to fill missing details in data. The issue is these methods focus only on single modality. What if we add images to the process of point cloud reconstruction? This transforms this challenge into multimodal problem, enabling us to achieve significantly higher fidelity in reconstruction. This brings us to ObitoNet, our proposed multimodal approach for high-resolution point cloud reconstruction. It combines the strengths of two modalities, point clouds and images.
Hey everyone, now I'll discuss the methodology and the architecture of the overall project. So this is the overview of the architecture, where you can basically see that we have three separate models, namely the ObitoNet PC, ObitoNet Image, and ObitoNet Cross-Attention Decoder. The ObitoNet PC handles the generation of point cloud tokens, whereas the ObitoNet Image handles the generation of image tokens. And these are both fed to a cross-attention decoder, which applies cross-attention between the tokens and generates a reconstructed output. To generate the dataset, we derived it from the Tanks and Temples online dataset. We used clip directly, and if the similarity was beyond a certain threshold, we selected that pair as to be fed to our model.
Yeah, coming to the ObitoNet point cloud encoder, to generate encoded tokens from point clouds, we first apply this algorithm called furthest point sampling and KNN to form n groups of point clouds. The way we get the tokens from these groups is by using a mini PointNet encoder, where we use the latent representation as our tokens. These tokens are passed to our point cloud encoder, which is a transformer based encoder architecture, which gives us the same number of tokens at the end as well, but they are encoded. Moving on to the image model, to get the encoded image tokens, we perform the same thing. We use two VIT pre-trained models, and we fine tune it for our particular instance. We patchify it, we get image patches. Image patches goes to the tokenizer, we get tokens, and then we get encoded image tokens by passing it to the image encoder. Now coming to the cross-attention decoder mechanism, we take both of these tokens from different modalities and we pass it through a cross-attention block. And then the output of the cross-attention block is a set of tokens that actually encodes both the information from the image modality and the point cloud modality. We pass this through a series of self-attention decoder blocks and a reconstruction head attached to gain the number of points back from the tokens. Yeah, so moving on to the results, we can talk about the chamfer loss. That's our metric for dealing with the similarity of point clouds. So we have a ground truth point cloud set, and we use the chamfer loss between these point sets to figure out the similarity between them. Moving on, to talk about the outputs, this is our baseline. This is what we're competing against. You see the ground truth on the left, and you see the masked portions in the middle. And PointMAE does well. It tries to reconstruct as much as possible, but obviously, it doesn't have the added modality, so we see it very sparse. So moving on to our ObitoNet base, we again, like I said before, we have the ground truth on the left, we have masked portions in between, and we have a reconstructed output on the right. As you can see, we have better reconstruction on the right, and it fills in gaps in a better way. Something that I really want to talk about here is the attention maps. So the y-axis is the point clouds and the x-axis is the images. So you can clearly see that all the tokens in the point clouds are attending to specific portions in the image, and this is what we'd like to highlight with these graphs on the right. Moving on to ObitoNet large, it's just more tokens, more everything actually. But as with larger models, it needs bigger data to train and more epochs, which is why you can see our matrix is very sparse.
So to discuss the outputs of the VIT MAE model, as can be seen here as well, the reconstruction outputs are quite clear. We have a much greater deal of clarity between the outputs. And again, in the cross-attention block, we are able to see a much richer attending between the queries and keys.
Yeah. So moving on, this particular model ObitoNet is because Obito is a character who is masked in Naruto and he has extensive vision capabilities and his visual prowess is unlimited. So that's why we call it ObitoNet.